Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome to another lecture on Matlab simulation of sliding mode control. Today we are going to discuss this research paper, a general framework for switched and variable gain higher order sliding mode control. This paper is an early access version of an accepted article. So this article has technically not been published yet, but this has been accepted for publication in the IEEE Transactions on automatic control. So what you are looking at is a preprint of this paper. So basically this is the latest development in higher order sliding mode control, and today we are going to see how we can develop Matlab code for this switched and variable gain higher order sliding mode control. So I'm not going to read through the paper. You can download it from the IEEE Explorer or purchase it from IEEE and read it yourself. So mostly this paper is addressing, of course, the serious drawback that is the chattering in sliding mode control, and how do you address that by proposing the higher order sliding mode control. So the switched and variable gain approaches are being developed in this paper for first and second order sliding mode controllers. And this is basically not a full length paper. This is a technical note, and it introduces a conceptual framework to merge the two aspects, providing a general methodology for the design and tuning of higher order sliding mode control. The main strength of the method is its generality, and in that it accommodates a generic order R sliding mode control, and it encompasses both continuous and discrete variation of the control parameters. The discrete variation giving rise to the switched strategies. So overall, well, there's an introduction of this paper, and then section 2 is the important section where the problem formulation has been discussed. The main system that is being considered by this paper is single input single output system, where you have x dot equal some function a of x and t plus some function b of x and t times u of t. So you can see that this system is linear in control input, and it has a single control input. U belong to R. States can be, so in general this can be nth order nonlinear system. And in order to apply the sliding mode control, first you have to define your output function. Output can be any nonlinear function of the state variables, and then there are certain assumptions for this paper. First of all, the assumption number 1 is that the output must have relative degree R. R can be 1, 2, 3 or any number. So output having relative degree R means that in the rth derivative of the output, the control input must appear. So if you take R times derivative of the output, it should look something like this: a function of state and time, h of x comma t, plus some function of g, which is also a function of state and time, times the input u. This is the first assumption, that the relative degree of the system should be R. Second assumption is that this function h and the function g in general will be unknown or uncertain, but their magnitude should have some upper bound, which might depend upon the state variable and also the time variable. So h of x, the magnitude of h of x comma t should be upper bounded by some function c of x and t, and g of x should lie in between the range k sub small m to k sub capital M. These are the functions of state and time, and in general the upper bound of this function k sub m is k bar m, and the upper bound of k sub capital M is k bar capital M. So in general these functions have to be bounded from above and below. This is another assumption. So these assumptions are basically telling you the type of systems for which the controller proposed in this paper will work. And similarly, there is something more about this C function and K functions. The objective, of course, of higher order sliding mode control is to make all the derivatives of the sliding surface equal to 0. So in this paper we assume that output is the output is the sliding surface, and the derivative of the output, let me show you here, it should be written somewhere around here. Let's see. So basically it's here. So you can see here that sigma sub I plus 1, which is the I plus 1 sliding surface, is defined to be equal to ith derivative of y, which means that the first sliding surface where I is equal to 0, sigma 1 will be equal to 0 derivative of y, which is y itself. So first sliding surface will be the output itself, second sliding surface will be the first derivative of the output, and so on. So rth sliding surface, the derivative of the rth sliding surface will be h of x plus g of x comma t times u, which is the rth derivative of this. Equation 3 is basically telling you that rth derivative of, if you compare equation 3 with equation 7, the derivative of sigma r is equal to rth derivative of y. Okay, then there is assumption 3 that the internal dynamics of the internal dynamics of this system must not have any finite escape time, and if you put sigma equal to 0 in these internal dynamics, then these internal dynamics will be called zero dynamics. So assumption 3 requires that the internal dynamics should not have any escape time with any possible value of the sliding surface, and when sliding surface is 0, the corresponding zero dynamics should be globally asymptotically stable. So this is another assumption or condition under which the work presented in this paper will hold, or the results presented in this paper will hold. When we do the numerical example, you will see more about the internal dynamics and the zero dynamics, and this there is more in this paper. We are not going to go into much detail. U of t is defined as discontinuous function, and this we are basically into section 2, which is after stating the 3 assumptions, it is moving on to there is another 4th assumption, that this discontinuous control capital U, which is a function of t and x, it should satisfy the following assumption, that this km is the lower bound on g of x function, which is the function that appears in the rth derivative of the output, and this c of x is the upper bound of h of x, which also is a function that appears on the rth derivative of the output. So this inequality should be satisfied, and also u should have some upper bound which is independent of the value of the state and time, which means that this is the ultimate value that can be reached by this function u, which is a discrete function. And this epsilon here in this equation 10, this is a positive constant, and of course u bar is also a positive constant. So if these 4 assumptions are satisfied, only then the results presented in this paper will be applicable. So once again, the assumption 1 is that the system should have relative degree r. Assumption 2 is where is assumption 2? This assumption 2 is that in the rth derivative of y, the function of state and the function of state that is independent of input and the function of state that is multiplied by the input, both functions must have some upper bounds. And similarly, assumption 3 is basically that the internal dynamics should not have finite escape time, and the zero dynamics must be asymptotically stable. All right, so then this fourth assumption is that this is some combination of the bounds on functions of state that appear in the RS derivative of the output, combined with the capital U, which is sort of like an input control input function. So it's not the final control law, but it is going to appear in the final control law. So U is some function of state and time which is discontinuous, but it must satisfy these conditions. And then once you find this U which satisfies assumption 4, then the control law is given by minus U of x comma t times the sine of the surface, this function S of sliding surface. So this sigma is basically a vector of all the sliding surface and its derivatives, sigma 1, sigma 2, sigma 3, and up to so on. Sigma, it will go till sigma r, I think. Yeah. So this S is a function of the sliding surface vector, and this S can be calculated. This paper has calculated S for first order, second order, and third order sliding mode controls. So if sigma is, if there is a single sliding surface, which means that the relative degree is 1 in the system. If R is 1, and the small r, which is the relative degree, this r, if this r is 1, then this is first order sliding mode control, which means that S of sigma is just simply equal to sigma 1, which is the sliding surface. And if our relative degree is 2, then the S of sigma will be this function of the two components of sliding surface, because for r equal to, sliding surface will have two components, sigma 1 and sigma 2. And then similarly, if for relative degree 3, this S of sigma is given by this expression. And you can also calculate S of sigma for higher values of R, but that those expressions will be become more and more complicated. So this is what has been mentioned in this paper. So far we have looked at the control law. This is the control law. This is the control law proposed by this paper. U of t equal minus capital U times sine of this S function of sigma, and this S function has been calculated for first order, second order, and third order systems, third order sliding mode control. And then this paper presents let me see, remarks, and then there is a, so this was the general framework. And after the general framework, here they have stated an interesting fact that if the relative degree of if the rth derivative of the output have another function which is a completely known function, then it does not matter, the results of the paper will still apply. So far we have assumed that both of these functions in the relative degree, in the expression for the rth derivative of the output, this is unknown and this is unknown. If there is an h bar function addition to these two functions, which is a known function, then the results of the paper will apply. That's what it's said in remark number 6. And then there are some constraints that have been discussed, that sometimes there are constraints on the state space and sometimes there are constraints on the sliding surfaces, and in those cases have been also discussed in this paper. So this is section number 3, which is also of interest to us, because in this section they have proposed the two specific control laws which are basically lie under this general framework. So this is the general framework control law. Where is it? This equation 12 is the general framework. U is equal to minus capital U sine of S of sigma. Under this general framework, there are two controllers that have been developed in this paper. One is the variable gain higher order sliding mode control, which is equation 29. So in variable gain higher order sliding mode control, the control law is given by this equation 12, but within the equation 12, capital U is given by equation number 29. So equation number 29 tells you that in variable gain higher order sliding mode control, how do you select the capital U? Here you can see C is the upper bound on the function, the magnitude of the function h of x, and Km is the lower bound on the function g of x, which appear in the rth derivative of the output, and this delta is some positive constant. So this is how you select capital U in variable gain higher order sliding mode control. And then there is another constant epsilon, which is Km times delta. This is also important in the control law because it appears somewhere here. You can see here this is 2 epsilon is appearing here. So this basically is in the variable gain case, this epsilon will be equal to you can see here epsilon is equal to Km times delta. And then there is switched higher order sliding mode control. In switched higher order sliding mode control, this h of x belongs to a range minus c I to. So in switched higher order sliding mode control, basically they assume that the state space of the system is partitioned into k non-overlapping subsets. So which are such that if you take union of all the subsets, they form the total state space. So if you go to equation number 7 here, let's see, yeah, here. So you can see here that this whole system, this whole sliding surfaces, if you create a manifold out of this, there are certain partitions of the manifold which are basically non-overlapping, and if you take union of all the partitions, then this becomes the whole manifold. Okay, so these are the assumptions under switched higher order sliding mode control, and within each manifold you have different control. So in the ith manifold you have control law Ci over Km comma I plus delta I. So there is a delta again is a positive constant. Km is the upper bound of the g function in the ith manifold, and Ci is the upper bound of the h function in the ith manifold. In the ith partition of the manifold, sorry. So there are partitions of the manifold, and then within each partitions epsilon is Kmi delta I. So again you will understand this in more depth when we do the this numerical example. So here is a numerical example finally for which we have we are making this video because we want to learn how to implement sliding mode control in the Matlab. So here we have a third order system. It is a third order nonlinear system. It has a control input U. It is a single input system because it has only one control input, and there is a disturbance D. So D is the unknown disturbance in the system which appears in the first and the second state of the system. And for this system, this basically there is a typo in this paper. Here x3 dot is x2, and this is here it is 2x2. Well, actually this should also be 2x2. So there is a 2 missing in this paper. It's a very small typo. It's also it is detectable. You can see easily that when you convert this equation 33 into matrix form, it becomes the a function becomes like this and the b function becomes like this. So this whole system comes is converted into form of equation 1 and 2. So then you have to define the output. Of course, here the output has been defined to be equal to state x3. So x3 is the output of the system which we basically want to make equal to 0, and then of course the output is equal to the first sliding surface sigma 1. The second sliding surface is the derivative of the first sliding surface, which is basically if you take the derivative of the derivative of x3. So x3 is the first sliding surface, so derivative of x3 is 2 times x2, which will become sigma 2, and if you take derivative of sigma 2, it becomes the derivative of 2 times x2. So the derivative of x2 is this whole thing, so this whole thing, and if you take the derivative of x2 and multiply it with 2, that becomes the derivative of sigma 2, which is the derivative of second sliding surface, which is written here. So since the control input appears in the second derivative of the output, therefore this system has a relative degree 2. So in the first derivative of the output is 2x2, and the second derivative of the output is this whole thing, which has the control input u. So relative degree is 2, and here if you compare this with equation 3 of the paper, where y rth derivative of y is h of x plus g of x times u, then g of x in this case is 1 because u has a coefficient 1, and h is the unknown function, which is d, and this whole term is a known term, which we can refer to as h bar, as here in remark 7. Here you can see that sigma r dot can be h bar plus h plus g of x into u. So in g of x is 1 in our example, h of x is d, and h bar of x is this whole thing in our example. Here you can see this 2 multiplied by 2x1 x2 plus sine of x2, this is h bar, and they have so yeah, this is h bar is equal to this, and h is equal to d, and you can see here that they have considered in this paper the constraint on the sliding surfaces. The constraint is that the magnitude of the sliding surface cannot be greater than 1. Neither the magnitude of sigma 1 nor the magnitude of sigma 2 can be greater than 1. So this is a manifold in which the sliding surfaces have to operate. And then this is an interesting step to find the internal dynamics of the system. So these are the these are the dynamics of the system in terms of the state variables, and that once you define the sliding surface, the internal dynamics must be independent of the control input u and the unknown input d. They define a diffeomorphism, which is an invertible function, such that x3 is equal to sigma 1, which we already know that sigma 1 is x3, then 2x2 is sigma 2, and they have defined 1 plus x1 minus 2 e raised to the power 2x2 to be equal to this variable zeta. So this has been defined very cleverly in such a way that when you formulate like zeta dot, the internal dynamics, then first of all there will be no control input or d appearing in zeta dot, because remember that, so I have calculated zeta dot for you here. So zeta dot, so since zeta is equal to 1 plus x1 minus 2 into e to the power 2 minus e to the power 2x2, if you look at this, then zeta dot is x1 dot minus 2 times e to the power 2x2 times x2 dot. So if you substitute x1 dot expression here and then x2 dot expression here, and then you remember that this x1 dot is x1 dot is this expression and x2 dot is this expression. So I have substituted them here in this equation, and then you simplify, and here you have x1 after simplification. So if you substitute x1 with 1 minus zeta plus e to the power say sigma 2, which comes from this diffeomorphism here, 1 plus x1, so this will be actually 1 plus zeta minus, So here there will be a plus here and a minus here. So sorry about that. So this will give you zeta dot to be equal to this expression that has been written here. Well, there is a not plus, this is minus. Sorry about this error. You can do it by yourself and you can verify this basically this equation is exactly correct, and you can verify that. So so once you have these, this is the internal dynamics of the system which you have calculated using this diffeomorphism, and once you put sigma 1 and sigma 2 equal to 0 in the internal dynamics, then you get the zero dynamics, and the zero dynamics is zeta dot equal minus zeta, which is asymptotically stable. So which means that the internal first of all, internal dynamics does not have a finite escape time, and secondly, the zero dynamics is asymptotically stable. So assumption 3 is satisfied. Assumption 1, 2, 3 all are satisfied because assumption 1 required that there should be a assumption 1 required that there should be a relative degree r. This system has relative degree 2, so assumption 1 is satisfied. Assumption 2 required that this h and this g must have upper bounds. Here g is equal to 1, so upper bound is easy, it is 1. Lower bound is also 1 for g, and h is equal to d, and once we specify d, we'll also be able to find the upper bound of h. So assumption 2 will be satisfied, and assumption 3 is about the internal dynamics, so it is also satisfied. Assumption 4 is about the assumption 4 will be trivially satisfied when we select the capital U to be from the equations proposed in the paper. So first of all, so this was the example so far where they have verified the assumptions. Then there is variable gain strategy. So in variable gain strategy, they have defined the d to be equal to nu times 1 plus sine t plus this whole function. So this is the d where nu is nu belongs to -1 to 1. So this is a random variable, so nu is randomly generated, so d nu is random, so this makes d to be random as well. So d is a sort of like a sinusoidal type function, but it is a random function. And then h is less than equal to, so since h is equal to d, so h will be less than equal to this whole thing. And since in this expression you can see that sine t cannot be greater than 1, so 1 plus 1 can be maximum equal to 2. Then this x3 is basically sigma 1, and sigma 1, for sigma 1 we have defined the constraint that this sigma 1 cannot be greater than 1, and sigma 2 can also be not greater than 1. So if you look closely, this x3 is sigma 1, and this 4x2 square, this is basically sigma 2 square. So sigma 2 can also be not greater than 1, so the square of 1 is also 1. So overall upper bound of this is equal to 4 in under this constraint, that the sliding surfaces cannot have magnitude greater than 1. So so we have specified each and everything. So capital U is equal to 1 plus sine t plus this. Where does this come from? This basically capital U comes from this equation, this equation number 29, because we have c of x equal to this whole term 1 plus sine t plus x3 plus 4x2 square magnitude. So this is c plus so they have selected delta to be equal to 1, so c plus delta is equal to capital U, and if you put like capital U like this, then you have the control law. Control law will be minus h bar minus u times sine of s of sigma. So remember that this is relative degree 2, so s of sigma will be this expression, they have also already shown it. Said this is the expression for S of sigma for relative degree 2 systems. So we have so this was all the build up. I think I have pretty much explained quite a bit. Then there are results, so it is time to get back to the results. I've already in order to save some time, I've already written the Matlab code, and I can show you how to write the Matlab code. So this is the Matlab function for the controller, the variable gain strategy controller. So if you look at this, first of all, the sliding surface S1 is equal to X3. So you already know from my previous videos that in order to implement the control, you have to define the function in Matlab and later on call it using ODE 45. So we define the function dx equal to variable gain sliding mode control VGSMC, and in this function we have sliding surface 1 equal to x3, which is basically this equation. You can see here in this paper sliding surface 1 is x3, then sliding surface 2 is 2 times x2, which is again from this paper, and then this E is basically epsilon, which is this epsilon, this epsilon which is to be appeared here. So this epsilon is km times delta, so delta is 1 and km is 1, so this epsilon is equal to 1. Capital U is 2 plus, so here capital U is 1 plus sine t plus this plus 1, so if you combine this one with this one you have 2, so 2 plus sine t plus absolute value of x3 plus 4 times x2 square. So this is capital U as presented in the paper, and then this is the control law, which is minus 2 times this is h bar, and then you have minus capital U times sine of this sigma 1 plus sigma 2 into absolute value of sigma 2 divided by 2 times epsilon. This is equation number 40 written here exactly in the same way, except that this is Matlab code and this is some equation in the PDF. So I have selected V to be random 1 minus random 1, which means that this random 1 generates a random value from 0 to 1, and this also generates a random value from 0 to 1. Overall, this difference will generate a random value from minus 1 to 1, as has been discussed in the paper. Then this is D function, which is V times 1 plus sine t plus absolute value, as has been described here in the paper. And then there is A vector, which is basically the same as here, so minus x1 plus 2 into e to the power. So this is A vector here, with all the 3 components. Notice that this is a column vector, so all the components are separated by the semicolon, and this is the B vector as presented in the equation 34 of the paper. So dx is equal to A plus B times U. U is calculated as in the paper. So this is the whole variable gain function, and in order to call this function I have also written the script file. So in this script file, you first of all, this is standard commands CLC and clear all, and then you have this is the options command for the ODE 45 function. It is up to you, you want to use this command or not. This is not necessary. I've just tried it. I've set the ODE set function, which sets the relative tolerance of the ODE solver to be 10 raised to the power minus 3, which is basically the default value for the relative tolerance. I have not changed the relative tolerance of this function. And then t comma x is equal to ODE 45 variable gain SMC. I am calling this function. So this function that I have written, I'm calling it in the script file, and then I'm running it from 0 to 10 seconds, because if you look at the results in this paper, so these are the results that we are looking to regenerate. So these are from 0 to 10 seconds, so that is why I have running it. So initial conditions are not given in this paper, but by closely looking at these figures you realize that this is the curve for x1. So x1 is probably initial value 0.5, and this is x2 initial value 0.3, and this is x3 initial value 0.8. I've just guessed these initial values from these figure. These are not given in the paper. So okay, once you run this command, you will have the you will have the state values and the time values. But in order to generate these other graphs, you need to write more code. For example, here you have to, once you have all the state values from solving the ODE 45, once you have the trajectory, then you can use this trajectory to recreate the sliding surface. So this is the sliding surface x1, which is the all values of the third state variable x3, and this sliding surface s2, which is 2 times all the values of so remember, this s1 and s2 are vectors, and this is very different from s1 and s2 in this function file. So in this function file, these are just scalars which are redefined with every new value of x2 and x3, but in this file we are defining them as vectors because we have calculated the whole trajectory using this ODE 45 command, and then s1 and s2 are recreated from the state variable trajectories. E is equal to 1 as before, u is the same, so these equations are the same. The only difference is that now this capital U is a vector which has all the values of x1, x2, x3 calculated from ODE 45. So this U is again the same equation, but difference is that you have all the values of x1. So this column means all the values of x1. So when you multiply these, you have to do component wise multiplication. Dot static is the component wise multiplication of x all rows and column 1 column with x all rows and column 2. So x all rows and column 1 is the all values of x1 in the state trajectory, and x column this 2 is all values of state x2 in the state trajectory. So you do this, and then so H is basically it is not straightforward to recreate H, because in here we have defined this random variable V which is generated inside this function file. To export this variable, you can do DLM write it in the text file, but this makes the code very slow, so I'm not gonna use that. I've already tried it. It makes the code very slow. And then you have this you can just create artificial value for this H function using this for loop, where you have V is equal to random1 minus random1 and HI equal this whole function as defined in the paper. So then you can plot t comma x, which will give you all 3 plots like this, and then you can also plot s1 versus s2, which will give you this plot. And then this is how you can plot a square in MATLAB. If you want to plot a square, then you can use this command. This I can also explain this command, but I mean it would be great if you figure it out on your own. This is very smart way of generating a square. I found it on the internet and I loved it. And so next is the plot of the control input U. So here this plot we are going to regenerate, and finally we are going to regenerate this plot of this 1 plus this whole function, which is basically this zeta function. So we are going to regenerate zeta as well, and let me show you. So zeta is so I've already run this file, and this is figure 1. These are my results. So if you look at these results and compare them with the original results of the paper, they are pretty much the same. Let me move this legend a little bit. Okay, so this is blue line is x1, the green line is x2. You can see that these are very similar to what is shown in the paper. This red line is x3, and this is the control input function, which is this blue graph, and the zeta graph is a little bit different. Mine is different from this paper a little bit. And also in my case, this graph, this sigma 1 versus sigma 2, it appears that it actually crosses it comes out of the square, which is not shown in the paper. So I'm not sure what's going on in here. So actually it does cross out of this square, but maybe there is an error in my code, because my zeta is also a little bit different from the zeta that they have. All right, so these are the results that you get from, I don't know, this is the 37 lines of code here, which is not a very difficult code, and then there's a 12 lines of code here. So within 50 lines of code you can regenerate the results of this paper. This paper also shows another controller. So for example, after this variable gain strategy, they have also shown switched gain strategy. So in switched gain strategy, they have created like two manifolds. S1 is so two partitions of the manifold of sliding surfaces. One partition is that you have a matrix of diagonal matrix where diagonal entries are 1 and 2. It's a 2 cross 2 matrix, and then if sigma prime, which is sigma transpose times m times sigma, if it is between 0.3 and 0.7, you are in S1. If it is less than 0.3, you are in S2, and if it is in neither of S1 and S2, you are outside S1 and S2. So they have selected capital U to be 2 when you are in S2, and 3 when you are in S1, and 5 otherwise. So you can write the code for so for example, let me minimize this. So this is the, so for switched gain strategy, the everything remains the same. Let me show you. Okay, this is the variable gain strategy. You can basically use the same code. So this is the switched gain strategy. You can see that S1 is the same, S2 is the same, E is the same. There's only difference is that you define the M diagonal matrix and you define the condition C. Condition C is that sigma transpose times m times sigma. Sigma is the vector of S1 and S2. So if this condition is less than equal to 0.3, then you are in S2. In that case, capital U will be equal to 2 as written here. And if it is not less than 0.3, if it is greater than 0.3 but less than 0.7, then capital U is equal to 3, and otherwise capital U is equal to 5. So there is only difference is that so you have these 5 lines in this switching controller instead of this single line in the variable. So code wise there is this difference, that capital U, instead of selecting it like this, you select it like this based on these conditions. So all other code remains same, and in this file you can just change the name from variable gain to SW switch gain. So you will have if you run this, you will get the results that are corresponding to switch gain. And then the third and final control that is discussed in this paper is the constant gain controller. So in the constant gain, they have used just capital U equal to 5. So that is the easiest one to implement. So if you go here, this is the code for constant gain controller. So if you compare this with the variable gain controller code, the difference is that instead of using this whole equation for u, you just set u equal 5 for everything, for every case. So this is the constant gain. So you can basically write this code, get this. These are the results for the constant gain controller. You can see that the control signal is very large, and these are the results for the variable the switched gain controller, and these are the results that we have already recreated for the variable gain controller. So you can see variable gain controller basically probably gives you the least amount of control effort, and this requires more effort in order to do the same task, and this requires the most expensive controller in terms of control magnitude. So I was I did not show you this h function, which is plotted here, but I have basically plotted h function in a different manner, so that I have shown you like this. So if you plot the h function in this manner, which I have done in this script file, then this is basically how the h function looks like. So this is the plot of h function versus time, which has been created using the same equation given in the paper. So there is some remarkable similarity between the shape of the h function and the shape of the controller. So obviously basically this h function that we have plotted is not the actual h function, because actual h function based on which the trajectories have been created is inside. So this d is equal to h. So this is inside the function file, which we could not we could retrieve using this dlm write command, and then using this dlm read on the other end. But I'm not going to go into that, because that makes the code run very slow. So I have instead plotted a sample of h function, if you will. So that's it about today's lecture. Today we have discussed the Matlab code for variable and switched and constant gain sliding mode, higher order sliding mode control. To be precise, it was a second order sliding mode control, and we have also discussed the main results of this paper, and I hope that you were able to grasp some of the things that I have talked about. Do get a hold on this research paper. It's a very good paper, and try to recreate the results using this video, and let me know if you have any problems or questions. Thank you for watching.